Hello viewers, in today's class we are going to discuss yet another important problem from application of derivatives, right? And here we are going to discuss this important inequality in which we have to prove that the tangent of x is greater than x for all x belonging to the closed interval 0 to pi by 2, right? So to prove this inequality, let us take a number c which belongs to the interval 0 to pi by 2, right? So here we assume a real number c such that c is greater than 0 but it is less than pi by 2, right? So to prove this inequality, this is the first step, right? Now the second step is to assume a proper function or an appropriate function, right? So let us assume a function f of x such that tan x minus x, right? So here we'll assume this function, right? F of x is equal to tan x minus x for all x belonging to the interval 0 comma c, right? Okay, so now what we will do, we'll differentiate this function f of x, right? So let us find out the derivative of f of x. So f prime of x is equal to d by dx of tan x minus x, right? Now we know that the derivative of tan x is secant square x and the derivative of x is 1, right? So the derivative of this function tan x minus x is equal to secant square x minus 1. And here we'll make use of one important trigonometric identity, that is 1 plus tan square theta is equal to secant square theta, right? So tan square theta is equal to secant square theta minus 1, taking this one to the right hand side, right? So secant square x minus 1 can be replaced by tan square x, right? Okay, so we have got this derivative. So now we have the derivative f prime of x is equal to tan square x for all x belonging to the open interval 0 comma c, right? And we can easily see that this derivative, that is f prime of x, is greater than 0, right? For all x belonging to this interval 0 comma c, right? Because c itself, it lies between 0 and pi by 2, right? So c lies in the first quadrant, right? And we know that in the first quadrant all the trigonometric functions are positive, right? So this derivative, which is equal to tan square x, is always greater than 0 for all x belonging to this interval 0 comma c, right? And moreover, tan square x being a square term, it is always greater than 0 for all x belonging to the interval 0 comma c, right? So we conclude that this function has the derivative positive, right? So the derivative of this function is a positive quantity, and which indicates that this function f of x is an increasing function, right? Because we know that if the derivative or the slope is positive or greater than 0, then the function is said to be an increasing function. So now here let us apply another definition of increasing function, right? Now see, if we have 2 points x1 and x2 belonging to the domain of the function, say f of x, right? And if x1 is greater than x2, then the definition of increasing functions says that f of x1 should also be greater than f of x2, right? So if x1 is greater than x2, then the value of the function at x1 should be also greater than f of x2. So now let us take x1 as x, right? And x2 as 0. So from this inequality, we have x greater than 0, right? So here we are assuming 2 points x1 and x2 as x and 0, right? And if x is greater than 0, then by definition of increasing function, f of x1 should also be greater than f of x2, right? So we should have f of x greater than f of 0, right? And we can see that f of x is equal to tan x minus x, right? And f of 0 can be obtained by taking x is equal to 0 in this function. So f of 0 is tan 0 minus 0. So tan 0 is 0. Here we have 0, so this is 0, right? So f of 0 is equal to 0. Now if we take this negative x to this right hand side, we'll get 10x is greater than x, right? So this is the desired inequality which we have to prove.